welcome you all in this course of Electronics Engineering, and the code of the subject is KOE038, and this is lecture number 2 of unit number 3. In the last class we were discussing about the transistor action, in which we have seen how the transistor is going to operate in emitter bias and collector bias junction. So if we want to operate the transistor in active region, we have seen emitter based junction must be forward bias and the collector based junction must be reverse bias. Is forward biased and the collector based junction is reverse bias. And now we will discuss how the transistor can be used as an amplifier. It is well known to all of us in the previous lecture, as we have discussed, transistor can be used as an amplifier in active region, in which emitter based junction must be forward biased and the collector based junction must be reverse biased. Now here we will discuss how the transistor is used as an amplifier. Now for the sake of simplicity, what we will do, we will understand the working of amplifier with the help of common base configuration, in which base is common for the emitter as well as for the collector terminal. So I am going to draw the circuit of transistor amplifier. This is basically PNP transistor. Here emitter based junction must be forward bias, because this terminal is known as a emitter, this terminal known as a base, and this terminal is known as a collector. So base is common. And let us assume the value of load resistance, which is defined as here RL. RL is given as a 5 kilo ohm. And let us assume the input resistance Ri is equal to 20 ohm. And the output resistance R0 is equal to 100 kilo ohm. Because it is well known to all of us, if the emitter based junction is forward biased, what is going to happen? The forward resistance is very small, because in the first unit we have discussed for the forward bias condition the resistance is very small. So input resistance is small, and this is your output resistance. As we know, the collector based junction is reverse bias, that means the output resistance is very high. And here we are assuming the load resistor, where you want to determine an output voltage, and let us assume this voltage is known as VL. The resistance is equal to 5 kilo ohm. So across this load resistance, what we want to do, we want to determine the load voltage across this load resistance, and the load resistance value is equal to 5 kilo ohm. This is your depletion region. I am not going to show over here there is a negative immobilizance, positive immobilizance, because we are interested how the signal is going to amplify. So let us assume the signal which we want to amplify, it is given as 200 millivolt. So the input signal strength is here is 200 millivolt, and that signal strength is very weak. What you want to do, we want to amplify this input signal. That means we want to enhance the strength of input signal. So how it is possible? With the help of transistor, let me describe you. So this is your P region, this is your N, and this is P. The construction of the bipolar junction transistor has been discussed in the previous lecture. Now let us assume the input current is here given as I, and the output current is given as IL. Is that clear? For the sake of simplicity, we are assuming the base current here IB is approximately equal to 0. So here this is input AC signal whose value is 200 millivolt, and we want to amplify it. That means we want to increase the voltage level, the voltage strength of such a weak signal, so that our instrument will able to detect that weak signal. So how the amplification is done with the help of P and P transistor, we will discuss it. So let us assume the input current is II and the output current is IL, and this IL current is known as a load current. And for the circuit, it is well known to all of us, this is your AC supply. Now the question arises, what about the DC supply? Here we are interested in only AC response. So here the DC power supply is not shown over here in this circuit, because our aim to amplify the input AC signal. We are not interested in DC response. We are interested in AC response. Is that clear? So for that purpose, I am not showing over here DC voltages. Is that clear? So input signal is VI and the output signal is VN, which we want to determine. Now here, let us assume, if you want to determine the input current, which we are assuming II, if you want to determine it according to the Ohm's law, this is equal to VI divided by RI. Is that clear? What is the value of VI? Here VI is equal to 200 millivolt. VI is equal to 200 millivolt, and the value of input resistance RI, as you can see, it is equal to 20 ohm. 20 ohm. So what would be the value? 0 would be cancelled out. This is equal to 10 milliampere. Sorry, 10 milli. Okay, I we want to determine 10 milliampere. So according to the Ohm's law, I is equal to V divided by R. Here V is equal to 200 millivolt, and the value of resistance, input resistance, is equal to 20 ohm. So the current which is basically allowed to flow through the device is equal to 10 milliampere. And it is well known to all of us, for the ideal transistor, if we are assuming the value of alpha, if we are assuming the value of alpha AC is equal to 1, if we are assuming the value of alpha AC is equal to 1, that means the value of current gain equal to 1 for the ideal transistor. In such a case, it is well known to all of us, IC approximately equal to IE. IC approximately equal to IE, because for the active region, it is well known to all of us, whenever emitter base junction is forward bias and the collector base junction is reverse bias, it is well known to all of us, input and output current both are equal. That means the collector, the current which is flowing through the collector terminal is equal to the current which is flowing through the emitter terminal. That means IC approximately equal to IE. Let me remove this circuit so that you can better understand what is going to happen in the mathematical analysis. So here, the value of input current, that means II, is equal to VI divided by RI, 200 millivolt divided by 220 ohm, and this current is equal to 10 milliampere. And for the ideal transistor, we are assuming alpha AC is equal to 1. And for the active region of operation, IC is approximately equal to IE. That means load current, the current which is flowing through the load, is equal to the input current. So here IL is equal to II. Is that clear? It's very simple. Now here what you want to do, if the current which is flowing through the load resistance is known to us, you can determine the load voltage. So what would be the value of load voltage? IL into RL, and this is equal to 10 milliampere. Now here IL is equal to 10 milliampere, RL is equal to 20 kilo ohm, or maybe it is, I think, 5 kilo ohm. If we will multiply it, the K will be cancelled out with the milli, that means 10 to the power minus 3 and 10 to the power 3, and we will get 50 volt. The output voltage across the load resistance is equal to 50 volt. Now here, we will discuss about the amplifier. If this is your amplifier, and we have applied voltage over here VI, which is equal to 200 millivolt, what we are getting at the output terminal, V0 is equal to 50 volt. So input signal resistance is very weak, and with the help of PNP transistor, as you can see, we can increase the signal strength. That means we can amplify the weak signal with the help of PNP transistor. Is that clear? So it is very simple. We are assuming the transistor is ideal. That means the current gain is equal to 1, alpha S is equal to 1. In such a case, emitter current is equal to the collector current. So the load current is equal to the input current. If the value of resistor is known to us, you can determine the output voltage as well as the input current and output current. Now, we will discuss about transistor configuration, or you can say BJT bipolar junction transistor configuration, or you can say transistor configuration. Is that clear? Now it is well known to all of us, as far as transistor is concerned, in the transistor we are having 3 terminals. First terminal is defined as emitter, second is base, and the third one is collector. Emitter is basically used to emit the charge carriers. Collector is used for collecting these charge carriers which is being transferred by the emitter, and out of these terminal, base is your controlling terminal, which is your third terminal. So with the help of base, output current can be controlled. So basically transistor is defined as a current control device. The output current can be controlled with the help of input current. As far as active region is concerned, if the input current is 1 milliampere, output current is also 1 milliampere. If the input current is 2 milliampere, that means output current is also 2 milliampere. Now here in this topic, we will discuss the different type of configuration. As it is well known to all of us, in the transistor we are having 3 terminals. If one of the terminal is made common, I am again repeating, if one of the terminal is made common, then the transistor can be utilized as 2-port network. Is that clear? So here, transistor can be utilized as 2-port network. So here, this is your input port, and here, this is your output port. So we have to apply the input voltage at the port number 1, and we are getting the output voltage at the port number 2. And similarly, this is your input current and this is your output current if one of the terminal is made common. If one of the terminal of transistor made common. So if you will make one terminal is common, transistor can be utilized as 2-port network. And depending upon, it's very important, you should always keep this point in your mind in well manner. If one of the terminal is made common, there could be a possibilities of 3 configurations. So depending upon which terminal you are making common, for the input as well as for the output, there are 3 configurations. Is that clear? So which terminal you are making common, based on that, there are 3 configurations of transistor. The first configuration is known as common base configuration, or you can say CB. Configuration. And the second configuration which could be possible is common emitter configuration, and that configuration is also defined, or you can say known as CE. CE configuration. And the last and the third one is common collector configuration, or you can say CC CC configuration. Is that clear? So as in the transistor, we are having three terminal, emitter, base and collector. Emitter can be common for the base and collector. Base can be common for the emitter and collector. Collector terminal can be made common for the emitter as well as for base. So we are having three configuration: common base configuration, common emitter configuration, and the common collector configuration. Each configuration will have a specific application. Is that clear? The application detail we will discuss after some time. But now I will define how we can draw the common base configuration. What are the various advantages of common base configuration? Is that clear? So let me describe you, or we will start with common base configuration. Common base. So here now we will focus on common base configuration. Common base configuration. So as the name implies, common base. So which terminal is common over here? Base terminal is common for the emitter as well as for the base. Is that clear? Now I am going to draw the common base configuration. The base is common. You can draw the common base configuration with the for NPN transistor as well as for the PNP transistor. Is that clear? I will draw the common base configuration with the help of NPN transistor, and at your home you can draw the common base configuration for PNP transistor by itself. Is that clear? Now look at here. Let us assume this is N region. This is your depletion rate. It will contain the positive immobile ions as well as negative immobile ions. But I am not going to showing it. Is it clear? This is P, and here this is again depletion rate. So here, which terminal is common? Base is common. Base is common for the emitter terminal as well as for the collector terminal. In all the configuration of transistor, whether there is a common base or you can say common emitter or common collector, all these configuration we will apply a active region. That means emitter base junction is forward bias and collector base junction is always reverse bias for all these configuration. So emitter base junction is forward bias and the collector base junction is reverse bias for all these configuration. Is that clear? Which are possible for the given BJT, that means transistor. Is that clear? Now look at here. This is your depletion region. This is your base region, and that region is known as a collector region. So emitter base junction must be forward bias as far as active region is concerned. Is that clear? So this junction must be forward bias. That means N must be negative with respect to base terminal, and here we are having RE. RE is your emitter resistance, basically control, you can say the current control resistor. We can limit the value of current. Similarly, we are having RC, current limiting resistor, and collector base junction must be reverse bias. That means N terminal must be positive. Is that clear? This is positive, this is negative. So here, this is reverse bias, and here, this is forward bias. For the active region of operation, it is well known to all of us, emitter base junction must be forward bias and the collector base junction must be reverse bias. Is that clear? And this is your depletion region. Now what is going to happen over here? As you can see, we will apply the input voltage at the emitter terminal with respect to the base terminal, and that input voltage is known as VBE. Or you can say base to emitter voltage, and you can also write over here VEB, voltage at the emitter terminal with respect to the base terminal. So we can write over here also VEB, voltage at the emitter terminal with respect to the base terminal. So input voltage we will apply at the emitter terminal, and the output voltage which we are getting over here at the collector terminal, and that voltage is known as a VCB. That means voltage at the collector terminal with respect to the base terminal. So input is going to apply at the emitter terminal with respect to the base terminal, and output which we are obtaining over here at the collector terminal with respect to the base terminal. Now what is going to happen? As soon as you will apply a forward bias voltage, the electrons, which are the majority charge carriers, we have already understood the working of the transistor in detail. So if you will apply a forward bias voltage, electrons are going to repel over here. Now this is the direction of current, emitter current, in the opposite direction of the flow of electron. Now here collector will collect these majority charge carriers is being injected by the emitter terminal. Is that clear? This is the movement. Now if this is the direction of electron, what will be the direction of collector current? In this direction, IC. And let us assume few of electron into the base region are going to attract by the positive terminal. So if this is the direction of electron, the current will be flow in the opposite direction, IB. So if you will apply KCL rule, that means I is equal to IB plus IC. I is equal to IB plus IC. This is simply KCL law. But as far as transistor operation is concerned, IC is equal to alpha times IE, where alpha is current gain, where alpha is current gain in common base configuration. It is very important. Alpha is current gain for the common base configuration, and sometimes this alpha can also define as a current amplification factor. So here alpha is equal to the current gain, and this alpha value is lying between 0.95 to 0.99. The value of alpha is basically depending upon the thickness of the base. If you will decrease the thickness of base, more charge carriers without recombine into the base region will be collected at the collector terminal. Alpha is going to increase if the base thickness is less, and the alpha is going to increase whenever base thickness is less. But if you will increase the thickness of the base, there are more recombination of electron and holes. So somewhere the value of alpha is going to decrease. The number of electrons which are transferred at the collector terminal are going to decrease, and the IC is also going to decrease. So here IC is equal to alpha times IE. If it is not equal to IE, so IC is equal to alpha times IE as far as active region is concerned. And this alpha is very close to 1. Now, what is going to happen if this base is open? If emitter is open, now what is going to happen if your input is open? That means emitter circuit is open. In such a case, there is no transfer of majority charge carriers. If your input junction, that means emitter is open. Now look at here, this emitter is open and this is your reverse bias voltage. Majority charge carriers are not able to move due to the barrier voltage. But the minority charge carriers, here the minority charge carriers are holes in this N region. So these holes get attracted by this negative terminal. So if the holes get attracted by this negative terminal, what would be the direction of the current? And this current is known as a reverse leakage current. So this is the direction of current, and let us assume this current is defined as ICBO. So the reverse leakage current, because this is your reverse bias voltage, and in the reverse bias condition, reverse current is flowing, and if we are assuming this is the direction of reverse current, because the holes, look at here, this is the direction, because the current is always flowing in the direction of holes. In which direction holes are flowing? the same direction the current is going to be flowing. So this is the direction. The holes are get attracted by this negative terminal. So this is the direction of ICBO, and this ICBO is known as collector to base leakage current. Let me describe you. ICBO is collector to base leakage current when emitter, or you can say input circuit, emitter is open. If the emitter is open, that current which is flowing in the reverse bias direction due to the minority charge carriers is known as collector to base leakage current. So here this is collector to base leakage current, and O stands for open. That means emitter is open. So this is the direction of ICBO, and in the same direction IC is also flowing. So somewhere reverse leakage current is going to be add on into collector current. So it will support to the collector current. So if you want to write the final expression, final current relationship, if you want to write the current relationship for the common base configuration, it is equal to, here IC is equal to alpha times IE. If IC is not equal to IE, that means IC is equal to alpha times IE, where alpha is closer to 1. And plus ICBO, collector to base leakage current, when the O stands for open, emitter is open. And in some books, it can also define as ICO. So this current is due to majority charge carriers. Majority charge carriers current. But if there is an absence of majority charge carriers, that means input is 0. In such a case, there is only ICBO. So this is basically reverse current, or you can say the reverse leakage current. So this is due to minority charge carriers. The current which is flowing in the reverse bias direction due to minority charge carriers, and we have already discussed in the unit number 1, and this current is depending upon the temperature. Reverse current is the function of temperature. So this is all about the common base configuration. Now we will discuss the input and output characteristic of NPN as well as PNP transistor for the common base configuration. Now here I will plot the characteristic of the NPN transistor for common base configuration, and at your home you can also draw the characteristic of PNP transistor in common base configuration. Now here we will discuss about the characteristic of transistor in common base configuration. Transistor characteristic. So as far as transistor characteristic is concerned, there are two types of characteristic: input characteristic. Second one is output characteristic. Is that clear? So firstly we will focus on the input characteristic. Is that clear? We will focus on the input characteristic. Input characteristic in common base configuration. Input characteristic in common base configuration for NPN. and transistor. So in the common base configuration, we want to draw the input characteristic. So in the common base configuration, the base is common for the emitter as well as for the collector. So here, if this is your emitter, this is your collector, base is common. The base is common for the emitter as well as for the collector. So what is your input current? IE. What is your output current? This is output side. Look at here. This is input side and this is your output side. So input current IE. Output current IC. Input voltage VEB. Voltage at the emitter terminal with respect to the base terminal. What is output voltage? VCB. Voltage at the collector terminal with respect to the base terminal. So we want to draw the input characteristic. Input characteristic is plotted between the input voltage and input current. I'm again repeating, input characteristic is plotted between input voltage and input current for the given value of output current. Sorry, output voltage. फिर से repeat कर रहा हूँ. I'm again repeating. Input current is plotted between the input voltage and input current for the given value of output voltage. So here, this is input voltage on this axis VEB in volt, and the input current is IE, and that current is plotted, or you can say this characteristic is plotted for the given value of output voltage, and the output voltage known as a VCB. And as far as input junction is concerned, it is simply PN junction. So we already know how we can draw the VI characteristic of PN junction diode. Because in the BJT, input junction is simply PN junction. So this is the characteristic. Now we have to define the value of VCB. How the VCB, if you will change, how the value of IE is going to be changed. So now let us assume this is your NPN transistor, this is depletion weight, this is VEB, and that voltage VCB. So if you will increase the reverse bias voltage, VCB is your reverse bias. Emitter base junction is forward bias, collector base junction is reverse bias. So if you will increase the reverse bias voltage, the depletion width is going to increase, and it will increase towards the base region, because the depletion region is always going to increase from higher doping to the lower doping, and the doping of the base region is very less. So that means depletion width is going to increase, so the base width is going to decrease. If the base region will decrease, more number of charge carriers get connected by the collector current. Because the recombination in the base region is going to decrease, because the base is now more thin. If you will increase the reverse bias voltage. So if you will increase the reverse bias voltage, collector current is going to increase. Is that clear? So here VCB is 10 volt. And you can write over here VCB is equal to 5 volt. So this is the input characteristic. Now we will discuss how we can draw the output characteristic. Output characteristic of NPN transistor in CB configuration. The output characteristic of the transistor is plotted between the output voltage and output current for the given value of input current. I'm again repeating, the output characteristic of transistor is plotted between output voltage and output current for the given value of input current. So on x-axis we are having the output voltage, VCE in volt, and on y-axis they are having output current IC. Because the base is common, output current is IC, and the output voltage is VCB. VCB. And the output current is IC. For the given value of input current, and the input current is IE. So let us assume here IE is equal to 0 milliampere, IE equal to 10 milliampere, IE is equal to 20 milliampere, IE is equal to 30 milliampere. Is that clear? Now, as far as active region is concerned, IC is approximately equal to IE. It is well known to all of us. IC is equal to alpha times IE plus ICBO. IC is equal to alpha times IE plus ICBO. So if IE is equal to 0 milliampere, so IC is equal to ICBO. That region is known as a cut-off. Cut-off region. As far as active region is concerned, IC is approximately equal to IE because ICBO is very small and alpha is close to 1. So as you can see, for the active region of operation, what is going to happen? IC is approximately equal to IE. This is a little bit slow because the ICBO is going to be add on into alpha times IE. So if IC is equal to 1 milliampere, if IE is equal to 10 milliampere, IC is also equal to 10 milliampere. If IE is equal to 20 milliampere, IC is also equal to 20 milliampere. If IE is equal to 30 milliampere, IC is also equal to 30 milliampere. So this region is known as active region. Active region. And in the active region, as you can see, input and output current are equal. So in the active region, transistor can be used as a constant current source. If input current is 1 milliampere, output current is also 1 milliampere. If input current is 2 milliampere, output current is also 2 milliampere. So here, the transistor in the active region used as an amplifier. The active region. Cutoff region, transistor is used as an off switch. Now what is going to happen in the saturation region? In the saturation region, it is well known to all of us. In the first lecture, I have explained to you, for the saturation region, emitter base junction is forward biased and the collector base junction is also forward biased. So for the ambient transistor, if this axis is 0, plus 1, plus 2 volt, plus 3 volt, plus 5 volt and so on, and if you will apply a negative voltage over here, minus VCB, if you will apply a negative voltage to the collector base junction, it is now behaves like a forward bias. So emitter base is forward bias, collector base also forward bias. Now what is going to happen in the forward bias condition? Look at over here. If your collector base junction is forward biased, now look at here. This is N, depletion region. This is P, depletion region. This is N, and this is forward bias. Collector base junction is now forward bias. If you will apply a forward bias voltage, in the forward bias condition, the depletion width is going to decrease. For the forward bias voltage, which is basically N is here, negative. Look at here, N is here, negative. If the collector base junction is forward bias, that means N is negative. So if you will increase the forward bias voltage and if you will apply the forward bias voltage, emitter base junction is also forward biased. So this is forward bias, this is forward bias. This is defined as a saturation. So in the saturation region, if you will apply a collector base voltage which is forward bias, depletion width is going to decrease. If your depletion width is going to decrease, the base region will increase. Recombination into base region also going to increase. Less number of charge carriers get collected by collector. So the collector current will decrease, it will reduce. So if this is minus 1 volt, minus 2 volt, minus 3 volt. Let us assume. So what is going to happen? Previously IC is equal to IE for the active region. Now the current for the forward bias voltage decrease, and that region is known as saturation region. Saturation region. So this is the output characteristic of NPN transistor for the common base configuration. And as far as common base configuration is concerned, current gain is less, but the voltage gain is high. So most of the time, the common base configuration can be used as an amplifier. The transistor is used as an amplifier in the common base configuration. Is that clear? Now we will focus on the common emitter configuration. Common emitter configuration. That means emitter is made common for the base as well as for the collector. Is that clear? As the name implies, common emitter configuration, that means emitter terminal is made common for the base as well as for the collector. We will apply the input voltage at the base terminal with respect to the emitter terminal, and we are getting the output at the collector terminal with respect to the emitter terminal. So emitter is common for the base as well as for the collector. And in the next lecture, we will discuss the detail of common emitter configuration, how we can draw this configuration with the help of NPN transistor and PNP transistor. Then we will focus on the current relationship for the common emitter configuration, and we will determine the relationship between the alpha and beta, where beta is your current gain, or you can say the current amplification factor for the common emitter configuration. Thank you.